Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to invite you to debate with me some features related to the construction of synchronous generators, and to do so I am bringing this text to serve as a basis for our conversation. Let me read the text and discuss the concepts. Synchronous generators. Synchronous generators or alternators are synchronous machines used to convert mechanical power to AC electrical power. Let me highlight this because it is exactly what this machine does. It converts mechanical power to AC electrical power. This power has to come from somewhere, and it comes from the mechanical power of water in hydroelectric power plants or of steam in thermal power plants. This chapter explores the operation of synchronous generators, both when operating alone and when operating together with other generators. This video is going to be about topic number 5.1, synchronous generator construction. This is what we are going to discuss here. In a synchronous generator, a DC current is applied to the rotor winding, which produces a rotor magnetic field. The rotor of the generator is then turned by a prime mover, producing a rotating magnetic field within the machine. This rotating magnetic field induces a three-phase set of voltages within the stator windings of the generator. In words, this is exactly what we need to do, what we need to know about generators. Everything is there in words, okay? Other than this, we have to work with equations that describe the operation. But in words, this is everything. In a synchronous generator, a DC current is applied to the rotor windings to create the rotor field, which produces a rotor magnetic field. The rotor of the generator is then turned by a prime mover, a turbine, producing a rotating magnetic field within the machine. This rotating magnetic field induces a three-phase set of voltages within the stator windings of the generator. Okay? When the rotor, the electromagnet, is rotated, it's going to induce voltages within the stator windings of the generator. Okay? Two terms commonly used to describe the windings on a machine are field windings and armature windings. They are different. Let's talk about them and see the difference. In general, the term field windings applies to the windings that produce the main magnetic field in a machine. In a generator, the field windings are in the rotor. And the term armature windings applies to the windings where the main voltage is induced. In a generator, the armature windings are mounted on the stator. For synchronous machines, the field windings are on the rotor. Here, the text explains it. For synchronous machines, the field windings are on the rotor, so the term rotor windings and field windings are used interchangeably. Similarly, the term stator windings and armature windings are used interchangeably. The rotor of a synchronous generator is essentially a large electromagnet. The magnetic poles on the rotor can be of either salient or non-salient construction. There will be pictures about this. Wait a moment. The term salient means protruding or sticking out, and a salient pole is a magnetic pole that sticks out from the surface of the rotor. On the other hand, a non-salient pole is a magnetic pole constructed flush with the surface of the rotor. A non-salient pole rotor is shown in figure 5-1. Here, this is a non-salient two-pole rotor for a synchronous machine. While a salient pole rotor is shown in figure 5-2. Let's go there and see. Okay, here it goes. This is a rotor with salient poles. This is a rotor with salient poles. A salient 6-pole rotor for a synchronous machine. Photograph of a salient 8-pole synchronous machine rotor showing the windings on the individual rotor poles. Picture C, a photograph of a single salient pole from a rotor with field windings not yet in place. So this is only the pole. The windings are not in place yet. And letter D, a single salient pole shown after the field windings are installed but before it's mounted on the rotor. Non-salient pole rotors are normally used for 2 or 4 pole rotors, while salient pole rotors are normally used for rotors with 4 or more poles. Okay, then this is what the text is saying. If your machine has only 2 or 4 poles, it's going to be of non-salient pole rotors. And if your machine has more than 4 poles, it's going to be of salient pole rotors. Because the rotor is subject to changing magnetic fields, it's constructed of thin laminations to reduce eddy current losses. Okay, this is important. The rotor is going to be constructed of thin laminations, and they will be insulated from each other to reduce these losses here, losses due to eddy currents. A DC current must be supplied to the field circuit on the rotor. Since the rotor is rotating, okay, the rotor is not stationary. So it is difficult to supply current to something that is rotating. We need a technique. And what is going to be the technique that we are going to choose for our generator? There are two, and the text is going to speak about this. A special arrangement is required to get the DC power to its field windings. There are two common approaches to supplying this DC power. Number one, supply the DC power from an external DC source. Okay, there's going to be an external DC source, maybe an outlet, to the rotor by means of slip rings and brushes. We are going to use slip rings and brushes to input this power from an outlet to the rotor of the machine. And number two, supply the DC power from a special DC power source mounted directly on the shaft of the synchronous generator. Now let's specify these two alternatives. Slip rings are metal rings completely encircling the shaft of a machine, but insulated from it. One end of the DC rotor winding is tied to each of the two slip rings on the shaft of the synchronous machine, and a stationary brush rides on each slip ring. A brush is a block of graphite-like carbon compound that conducts electricity freely, but has very low friction, so that it doesn't wear down the slip ring. If the positive end of a DC voltage source is connected to one brush and the negative end is connected to the other, then the same DC voltage will be applied to the field winding at all times, regardless of the angular position or speed of the rotor. So this is the technique used when we use lip rings and brushes. This is what is done when it's necessary to use lip rings and brushes. Slip rings and brushes create a few problems when they are used to supply DC power to the field windings of a synchronous machine. They increase the amount of maintenance required on the machine, since the brushes must be checked for wear regularly. In addition, brush voltage drop can be the cause of significant power losses on machines with larger field currents. Despite these problems, slip rings and brushes are used on all smaller synchronous machines. If your generator is small, you are going to need to use slip rings and brushes because no other method of supplying the DC field current is cost effective. Nevertheless, if your machine is large, then you're going to need to use another technique, and this is what we are going to describe now. Take a look at this. On larger generators and motors, brushless exciters are used to supply the DC field current to the machine. A brushless exciter is a small AC generator. Let's highlight this. It is important. A brushless exciter is a small AC generator with its field circuit mounted on the stator and its armature circuit mounted on the rotor shaft. The three-phase output of the exciter generator is rectified to direct current by a three-phase rectifier circuit, also mounted on the shaft of the generator, and is then fed into the main DC field. By controlling the small DC field current of the exciter generator located on the stator, it's possible to adjust the field current on the main machine without slip rings and brushes. So this is the main advantage that this technique provides. We won't need slip rings and brushes. This arrangement is shown schematically in figure 5-3. And a synchronous machine rotor with a brushless exciter mounted on the same shaft is shown in figure 5-4. Since no mechanical contacts ever occur between the rotor and the stator, a brushless exciter requires much less maintenance than slip rings and brushes. Let's analyze the picture. Okay. Here we have the stator of the exciter and the rotor of the exciter. The power is going to come to enter through the stator of the exciter. The exciter is going to produce the AC current, and this AC current has to be rectified before supplying the main field, the field of the main machine. Okay, so power is going to come from here, pass here, and exit here. Okay, after being rectified, it is going to go to the main machine, and when the main machine is rotated, the rotor of the main machine is rotated, it is going to induce voltages in the armature windings of the stator of the main machine. A brushless exciter circuit, a small three-phase current is rectified and then used to supply the field current of the exciter, which is located on the stator. The output of the armature circuit of the exciter is then rectified and used to supply the field current of the main machine. And the figure 5-4, can you see this rotor here? Very beautiful, isn't it? Very big, this rotor. Photograph of a synchronous machine rotor with a brushless exciter mounted on the same shaft. Notice the rectifying electronics visible next to the armature of the exciter. Okay, the exciter is here, and the rotor of the main machine is here. Later we return to figure 5-5. Let's see what the text says. To make the excitation of a generator completely independent of any external power sources, a small pilot exciter is often included in the system. You could see here in this picture here that we need, okay, a source of power here. We need to connect the exciter to an outlet. You can use an AC outlet and rectify, or you can use a DC outlet. And in this case, we need to rectify the signal. Okay? But now we want to make the excitation completely independent of any external power sources. And to do so, we need a pilot exciter. A pilot exciter is a small AC generator with permanent magnets mounted on the rotor shaft and a three-phase winding on the stator. It is a generator. It is a generator. This pilot exciter is an AC generator, but a little bit different. A little bit different because its rotor field comes from permanent magnets rather than from an external source. So the field comes from permanent magnets mounted on the rotor shaft and a three-phase winding on the stator. It produces the power for the field circuit of the second exciter, which in turn controls the field circuit of the main machine. If a pilot exciter is included on the generator shaft, then no external electrical power is required to run the generator. Let's return to figure 5-5. Okay, power is going to flow in this direction here. The field of the pilot exciter is going to come from the permanent magnets. It's going to induce voltages on its armature. The currents will be rectified, and then they are going to induce voltages on the armature of the exciter, the second exciter. They will be again rectified and fed into the rotor of the main machine. And this electromagnet, the rotor of the main machine with its field, will induce voltages in the windings of the armature of the main machine, and then these voltages will be used to supply for loads. Okay? The loads will be supplied by these voltages here that are induced in the stator windings of the main machine. Many synchronous generators that include brushless exciters also have slip rings and brushes. Why? Why would we need that? Here is the explanation. So that an auxiliary source of DC field current is available in emergencies. The stator of a synchronous generator has already been described in this book, okay? And more details of stator construction are found in Appendix B. We are not going to discuss this. Synchronous generator stators are normally made of preformed stator coils in a double A winding. The winding itself is distributed and coordinated in order to reduce the harmonic content of the output voltage and currents. As described in Appendix B, we are not going to discuss Appendix B. And lastly, a cutaway diagram of a complete large synchronous machine is shown in Figure 5-6. This drawing shows an 8-pole salient pole rotor, a stator with distributed double-A windings, and a brushless exciter. Okay, so this is the last of what we are going to discuss here. This is the main machine, okay, and here the exciter. Okay? Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed it. If you wanted to join the discussion about the construction of synchronous generators, simply leave a comment for us. Goodbye!